This is the second lecture of Chapter 18, which deals with pericyclic reactions. So in this presentation, we will do the following. First, we'll do a quick review of cycloaddition reactions, which we started in the last lecture, and we will continue in this lecture here. Next, we will cover the Diels-Alder reaction, and we'll go into another type of pericyclic reaction known as the electrocyclic reaction. And lastly, we'll look at the third type of pericyclic reaction, which is known as the Sigmatropic reaction. So let's start. So a quick review. There are three types of pericyclic reactions. The first that we looked at or started last lecture was the cycloaddition, which is basically the addition of two molecules which have double bonds. The classic one is that of the Diels-Alder, where there's a reaction between an alkene and a diene in the presence of energy to give a six-membered ring, which is also an alkene. That's a very important reaction in organic chemistry, and as we have seen, it's known as the Diels-Alder reaction. The next type of pericyclic reaction is the electrocyclic reaction. As we'll see in this lecture, it's basically a polyene, conjugated polyene, in the presence of energy. We'll discuss the type energy needed. Will give us a cyclic structure. So in essence, we're making a bond right here, and here's the bond. The last type pericyclic reaction is the sigmatropic reaction. And this is unique because in the presence of energy, this is not really a conjugated system, but it's noted that sigma bonds are broken. Notice there's a sigma bond here, and it's not here. And a sigma bond here in the product, and it's not here. So we'll discuss that in terms of how that reaction actually occurs. So let us begin. So we had looked at cycloaddition reactions last lecture, and we mentioned that they are stereospecific in that a specific stereoisomer as a reactant react to give a specific stereoisomer as the product. And one way of describing these reactions is to use numbers. So a 2 plus 2 represents the number of pi electrons in each reactant. So here is ethylene, 2 electrons, and here is cis-2-butene, 2 electrons, because here is a point of reaction. In the presence of light, it gives a cyclic product, which is a cycloaddition. The key here, though, is to note the stereochemistry of the product. These two methyl groups here are cis, so in the product, the relationship between these two methyl groups is cis also. So the stereochemistry is maintained in going from reactants to product. Here's another example. Same ethylene, but in this case we have trans-2-butene. So here the two groups are trans to the double bond here. In the presence of light, we have here the trans product as shown here. As we emphasized in the last lecture, light is important for these reactions. I should say light is necessary for these reactions because it promotes electrons so that the orbitals are allowed for the electrons to flow from the HOMO, highest occupied molecular orbital, to the LUMO, lowest unoccupied molecular orbital for both reactants. So you may want to review that concept again. In this lecture, however, we will concentrate on the Diels-Alder in a little more details. So as pointed out in the last lecture, it is a 4 plus 2. Why 4 plus 2? 4 pi electrons. So here 2, 4, and 2 for 2 right here. So it's a 4 plus 2, and it's a cycloaddition because these two reactants will be combining to form a cyclic product. As we have shown, we can use arrows to indicate electron movement. So these electrons coming out to form a bond right here, and here it is. And these electrons coming out to form a bond right here, and here it is. And these electrons moving in to form the double bond. So these electron movements will result in the transition state as shown here. So notice it's a 6-member ring transition state with 6 electrons in this ring. We'll emphasize the importance of the 6-membered ring with 6 electrons because you will recall if you have 6-membered ring in a ring, if you have 6 electrons in a 6-membered ring, that's very unique, and that's an aromatic system. So that's one of the driving forces for these reactions to occur. We mentioned that the last reaction, which is the 2 plus 2, requires light. For these reactions here, however, which is the 4 plus 2, heat is required. So as shown in the example here, we have the diene. Note again that these terms, this is the diene. As you can see here, we got them switched, but the same two reactants. This is the diene, and this is the dienophile. To refresh your memory, the diene has 1, 2 enes. And the dienophile, phile here means loving, so the dienophile loves the diene. So that's why a reaction occurs, because they attract to each other. So this is the product that results here, and you can do your typical electron movement to show that this is what happens to form the bond here. So these electrons move out to form this bond right here. These electrons move in to form this double bond right here. And these electrons move out to form this bond right here. So that's how your 6-membered ring is formed in the presence of heat, as we emphasized in the last lecture. What we'll do in this lecture, though, is to demonstrate that these reactions are also regiospecific. In other words, there are specific regions of the molecules where this reaction will occur. But first, it has been shown that if the diene is electron rich and the dienophile is electron poor, the reaction occurs readily. Let's see what that means. So here's the diene. We say if it's electron rich. So if we have a substituent here which has an oxygen which has a lone pair of electrons, in this case 2 lone pair of electrons, these electrons can donate this group can donate the 2 electrons to the diene, making it electron rich. So once again, so this diene has an oxygen that's adjacent to the diene. It has at least 1 unshared pair of electrons, Of course, as you know, drawing resonance structures, these electrons can be donated into the diene, just as we've seen before for the benzene system. So this means that this group here is an electron donating group. Electron donating group. Let's look at the dienophile. So the dienophile here, as shown, has this group bonded to it. This group here is an electron withdrawing group because here is a double bond to the electronegative oxygen, so these electrons can be pulled into the oxygen. So we say that this substituent here is an electron withdrawing group. So to summarize, if we have an electron withdrawing group on the dienophile, it makes that dienophile electron poor. If we have an electron donating group on the diene, it makes that diene electron rich. So as you can imagine, an electron rich group with an electron with poor group makes for a favorable reaction. So with this deals all the reaction here. Here's the 4, here's the 2. Let's highlight this. And here is the 4. 4 plus 2. We'll have a reaction like this. So here would be your product. As you can imagine, however, this molecule here can rotate, can flip 180 degrees up. So it's possible to have this as the product. But this is the major product. And of course, this is the minor product. So as you know, in organic chemistry, we are concerned primarily with the major organic product. The question now is, why is this the major product and this the minor product? So let's see. On the next slide, here we have the diene again and the dienophile. So what we have drawn here are resonance structures in which this electron donating group donate its electrons to the diene. So here we have this as negative, key here, that's negative. And if you pull electrons from this double bond to neutralize that positive charge, you can see this is partially positive. As you can imagine, this is nicely set up for a reaction because the diene here has this group bonded to it. So this is an electron withdrawing group, so these electrons can be drawn onto the oxygen here as shown here. So this is negative and this is positive. So as shown here, this is a nice setup for reaction to occur where the negative will react with the positive, and here these electrons here will come in and react with the partial positive. So this gives the major product here. So that's why we say this reaction is regiospecific, because this is the preferred arrangement. Let's look at the opposite arrangement. So here we have the other arrangement. So here's the same diene doing the same thing. We have this as negative up here and this as partially positive down here. But if the diene is flipped, and that's possible in a reaction because, you know, molecules are constantly moving around. So if it's flipped, it makes this the electron withdrawing group, pulling the electrons from the dienophile or the double bond into the oxygen as shown here, making this positive and this partially positive. You can see that will not work or is not favorable. This is negative, and as you can see, when these electrons come back in. This makes this carbon here negative, so that will not work, not very favorable. So this product here will not form, or if it forms, will be in a minor quantity. So that is why we say that these reactions are regiospecific, because they react at specific regions of the molecule. So let's apply that knowledge here. So here's some examples of the Diels-Alder reaction. So here we have the diene, and notice again, sometimes we'll put these electrons in and sometimes we won't, but at least you know they are there because you have your periodic table. So this is an electron donating group, making this electron rich, making this carbon here negative. Here's the dienophile, and here's the CN. Don't forget the CN here is C triple bonded to nitrogen. Nitrogen is electronegative, so it will pull the electrons onto the nitrogen, making this dienophile electron poor. So as you can see, this end here will be partially positive based on the electron movement onto the nitrogen. This end will be partially negative based on these electrons moving onto this carbon. So this is nicely set up for the Diels-Alder reaction, where a bond will form here and a bond will form here. And of course the major product is this. Notice the relationship 1, 2, 3, and 4. So it's a 1-4 relationship and not a 1-2. Let's look at this one. This is drawn differently here, but hopefully you realize that this carbon will not bond to this carbon here, because this group here is electron withdrawing group. It's an electron withdrawing group. So the reaction will not occur from here to give the 1-2 product, but from here to here. So you'll have to exercise extreme care in analyzing your reactants to make sure you form bonds in the right places. So you can see here, this is the major product. Again, the 1, 2, 3, 4, because this carbon bonds here and this one will bond here. So if you flip that, you will see that much clearer. So again, you should be able to predict the products of Diels-Alder reaction in terms of regiospecificity, and you should be able to predict the reactants, the diene and or the dienophile of the 4+2 Diels-Alder reaction. Let's look at another aspect of the Diels-Alder reaction. This one has to do with the stereochemistry here. So we say that they're stereospecific, these reactions are. So here's the dienophile and here's the diene. Notice the isomer here. This isomer here of the dienophile has both methyl groups on the outside of the double bond system. In other words, they are on the same side of the double bond system. In the 4+2 cycloaddition, these electrons will come here and here to form the product, but notice here, these groups are cis to each other on the same side. So the products could be this or this. Of course, it's just a matter of flipping the molecule, same molecule. Okay, but the main aspect is they are cis to each other here. Let's look at the other isomer. This is another isomer of the diene. where this methyl group is on the inside and this is on the outside. So again, bear in mind that this is a isomer, a different molecule known as isomer here. So here we have these electrons coming in and these electrons going out, and of course these electrons coming in to form a bond here and here. Again, notice that this, by the way, this is an error here. This should not be here, so let's take that out. So notice here that this stereochemistry is, since these are on opposite sides of the double bond, they are now trans to each other. So it's a trans arrangement. Okay, so you could do this, or notice the dash and wedge to indicate trans arrangement. So again, these are all the stereospecific reactions in which the products have specific stereochemistry based on the stereochemistry of the reactants. Look out for that, because you'll see questions such as give the major organic product and be sure to indicate stereochemistry where appropriate. Let's look at an example here. So here is the diene. As you can see, this is an electron-rich diene, which makes it a favorable reactant. Here is the dienophile, and notice it has two CNs. Remember, the CN is a C triple bond to the N. So it's electron withdrawing, which means that this dienophile here is a very reactive dienophile for the Diels-Alder reaction. Notice the stereochemistry of this dienophile. They're on this CN here and this CN here on the same side of the double bond. So therefore, after the reaction has occurred, the relationship is maintained. It is a cis relationship, and of course a six-membered ring. Here's another example. This is a cyclohexadiene, where this is the diene right here, but it's in the form of a ring. Here's the dienophile. The same CNs are here, making this a very reactive dienophile. So we'll form a bond from this carbon to this carbon, and these electrons will swing in to form this double bond here, and we'll form a bond from here to here, as shown here. So this will now become our six-membered ring right here. Hope you can see that, because this is the bond that's formed right here and right here, and this is our bridge right here. Again, notice the CN are on the same side, so that's why we put the CNs down on the same side. Here's another reaction. This is a cyclopentadiene drawn like this, but it's basically this molecule drawn like this. But just to demonstrate, this bond will react to form a bond here. These electrons will come in to form that double bond, and this bond will form here to form this bond right here. And of course, this part of the molecule will come along with it. So again, here's your six-membered ring right here. And here's the bridge. Here's the bridge. And here's the bridge. So again, you should be able to recognize dienes, such as shown here. Here's a diene. And the dienophile, such as shown here. So what's bonded to the dienophile, as you can see, just basically comes along with that reaction. Okay? All right, let us turn our attention now to another type, the second type of electrocyclic, pericyclic reactions, and this type is known as the electrocyclic reactions. So first was the cycloaddition, Now we're looking at another type known as this electrocyclic reaction. Let's see what it is, first of all, before we start doing our analysis. So these reactions involve ring closure and ring opening. They're reversible reactions where the ends of the polyene or the conjugated polyene form a bond, a sigma bond. So here are the ends of this polyene here, and it forms a sigma bond right here. As you can imagine, these electrons here move around and a new pi bond is formed here. So, electrocyclic, as the name implies, is a cyclic, so it forms a ring, as shown here. And it starts off with a conjugated polyene. So we're not looking at two reactants as we did for the cycloaddition. We're looking at just one reactant that's a conjugated polyene. Let's see how that works. Example, here is the conjugated polyene for 2,4-hexadiene. So here is the conjugated polyene in the middle. In the presence of light, it closes up to form this bond right here. Notice at the ends, that's where it closes up. In light, it forms the cyclobutene, but with special stereochemistry here. In heat, it also closes up, but notice the stereochemistry is different. It's a trans arrangement, and this is a cis arrangement. Look at the other isomer here. This is the other isomer of 2,4-hexadiene. So here's the other isomer shown right down here. So in the presence of heat, we get the closure right here and here to form the cyclobutene. And of course, since we have methyl groups bonded, here are the methyl groups. But notice here, this is cis. And in the presence of light, this is now trans. It looks confusing, but what we'll do over the next few slides is to explain this. But what I wanted to take from this slide is that these reactions are called electrocyclic reactions because there is a polyene and it closes here to form a cyclic structure. This can be initiated in either heat or light. That's the main key here, is that these reactions are initiated in either heat or light. If initiated in heat, we get one stereoisomer. If initiated in light, we get another stereoisomer. So you can see the importance of these reactions because, of course, as you know, a large percentage of natural products are in fact stereoisomers. So this gives you a good way of synthesizing these type molecules. So let's look at the effect of heat or light on the stereochemistry of these products. Okay, here's a little complicated slide, crowded slide, so let's walk it through. So this is the ground state of 2,4-hexadiene. So these are the molecular orbitals. Remember that there are 1, 2, 3, and 4 carbons that have double bonds, which are sp2 hybridized atomic orbitals. And of course, if you form molecular orbitals, you form 4 molecular orbitals, just as we did in the previous lectures. So these are the 4 molecular orbitals for 2,4-hexadiene, looking basically at the conjugated diene system. These are the 4. So we have 4 electrons. So in pi 1, the lowest energy, there are 2 electrons. In pi 2, the next energy of molecular orbitals, we have 2 electrons. And the higher orbital, there are none, because we only have 4 electrons in a diene. And of course, the 4th molecular orbital has none. So we have some terms that we introduced last lecture. This is the HOMO, highest occupied molecular orbital, and this is the LUMO, lowest unoccupied molecular orbital. So this represents the ground state. So what we're concerned with here is the HOMO. So as you can see here, an inspection of the HOMO, and I've redrawn it over here, right here, shows that for the closure of this carbon to this carbon, we have to, this bond here must in fact rotate so that its symmetry or phase allowed. So, as you can see, if we do a clockwise rotation, this over here and this over here, this comes here and this comes up over here. So that means that this is now phase allowed or symmetry allowed. Notice it's a clockwise rotation and a clockwise rotation. We call that type rotation a conrotatory ring closure, because both are moving in the same direction. What I want you to concentrate on next is these groups here. So here's the methyl group and here's the methyl group. By making that rotation, this methyl group comes on top and this methyl group comes on the bottom, which makes that relationship a trans. So let me just summarize, because it's a little involved concept here. So let's summarize. So the important orbital is the HOMO. Why the HOMO? Because that's where the 2 electrons are to make that new bond. Since we're looking at a ring closure between this carbon and this carbon, as redrawn here, there has to be a rotation around this bond. Let's look at this bond over here, around this bond right here, and this bond right here, so that these orbitals come in to have a phase allowed combination. As you can see, this happens here. In so doing, we'd have to rotate this and this bond in the same direction, clockwise. And that type rotation is called a conrotatory ring closure. In so doing, we have a trans arrangement of the methyl group. Let's look at the opposite. If we now have the excited state of 2,4-hexadiene, how do we create the excited state? We created the excited state by providing energy in the form of light. Light of specific wavelength will promote an electron from the HOMO, as shown before in the ground state, to here. So now we have the excited state where this orbital here is now the HOMO, highest occupied molecular orbital. So we'll concentrate ring closure on this orbital right here, and not on this one, because now this is the HOMO. I've redrawn it over here. Again, we need to have the phase allowed or the symmetry allowed overlap between this carbon and this carbon. To do that, we'll have to rotate this bond here in a clockwise manner. Notice clockwise in the direction of the clock. So So this will come down to here. And this one will be counterclockwise, so that this will come over here. So we have the phase allowed or symmetry allowed. In so doing, let's look at the methyl group. So this methyl group here and this methyl group here, this will now come on the same side, giving us a cis arrangement. This type ring closure is called a disrotatory because they're going opposite. So here's a clockwise going in this direction, and a counterclockwise in this direction. And that happens because we need the phase allowed orbital overlap here. So that's a disrotatory ring closure. And that gives the cis product. Okay, so let's summarize by looking at these reactions again. So we have here a 4-pi system in the same hexadiene. So here's the diene right here, 4-pi system, 2 electrons and 2 electrons make it 4-pi. In the presence of light, remember there's an excited state where the electron is promoted, and we have the HOMO as pi 3, and we need a disrotatory closure, and that will put the two groups cis to each other. For the other isomer, let's look at the other isomer here. If we still have a 4-pi system here, and now we're looking at heat, not light, so the HOMO will be pi 2. And in that case, we have a conrotatory ring closure, and that will bring these two groups here in a cis arrangement. So you'll have to exercise extreme care in analyzing the isomer of the polyene, in this case a diene, and the type ring closure based on the energy supplied. And that will give you your product. So let's look at here a summary. So this is a quick summary here. This will make it much easier to remember. So if you have 4 electrons in the pi system, supplying heat will give a conrotatory closure. If you have the same 4 pi electrons, in this case supply energy by light, it will be a disrotatory closure. Let's extend that reasoning. If you have 6 pi electrons, if you did all the analysis as we have done before, and you supply heat using the HOMO to get the phase allowed overlap, it will be a disrotatory closure. And of course, if you have 6 pi electrons and supplying energy by light, it will be a conrotatory closure. So again, this table will become very important in terms of carrying out or applying these concepts to predicting the product of reactions. And we have some examples on the next slide. So here are some systems here. This is a 6 pi electron system. So let's look at this. Why is it 6 pi? 2, 4, and 6. So using the previous table, we have light, and that would give us this type closure shown here. Notice that these groups here are on the same side of the double bond, so doing that type closure will give us the trans arrangement. Over here we have the same type arrangement, same 6 pi system, and we have the same type arrangement on the same side of the polyene here, And using heat, we'll have the opposite type closure, and then we'll have this cis arrangement. Let's look at the last one. This is the polyene as the reactant, and now we have the methyl groups on the opposite sides of the double bond, or opposite side of the double bond. In the presence of heat, the type closure will give us here the cis arrangement. So use the table that's shown on the previous slide to predict the product that's shown here based on the type energy and based on the number of pi electrons in the reactant. Okay, let's look at the last type reaction for the pericyclic reactions here. And this is the Sigmatropic reaction here. The name of this type reaction is called the Sigmatropic reaction. In this type reaction here, we have a sigma bond that's formed, and another sigma bond is broken. Okay, so let's think about that for a second. A sigma bond is formed and one is broken. This system here, let's use this as an example. This system here is not a conjugated system, but it has double bonds. So here we can see, here's a sigma bond here, and here's none. In the product, here's a sigma bond, and here's none. So this sigma bond here, let me highlight that, so this sigma bond here is broken to give the product, and this sigma bond here is formed to give the reactant. As you can imagine, if you're using arrows to show electron movement, the electrons here move out, here, and here to form a 6-membered ring cyclic transition state. Notice again, it's a 6-member ring cyclic transition state shown here. Why is that so important? As we emphasized, if you have a 6-membered ring and 6 electrons involved in that ring, it's a very stable situation here, very stable ring system. So this transition state is very stable, hence these reactions are very favorable. So let's look at some examples. So before we look at some examples though, let's look at the nomenclature for describing the sigmatropic reaction. So looking at the transition state for the previous reaction, this is described as a 3-3 sigmatropic rearrangement. Why is it 3-3? We know why it's a sigmatropic rearrangement, because a sigma bond is broken and a sigma bond is formed. But why is it 3-3? What we do is we identify the bond that's being broken, and we identify the bond that's being formed. And we start numbering from the bond that's been broken to the bond that's been formed. So 1, 2, and 3, and 1, 2, and 3. So the 3-3 indicates here that there are 3 atoms that are involved between the bond that's broken and the bond that's formed. 1, 2, 3 atoms, and 1, 2, 3 atoms. Hence, it's a 3-3 sigmatropic rearrangement. Let me do that again, just to ensure that we get it. Here's the bond that's been broken, and here's the bond that's been formed. We number from the bond that's been broken, 1, 2, 3, and the other carbon, 1, 2, 3. This is described as a 3-3 because there are 1, 2, and 3 atoms that are involved, or that are separated, I think that's a better word, that are separated from the bond that's broken and formed. 3 atoms separated from the bonds that's broken and formed, so it's a 3-3. Let's see if we can apply that to another system here. This is a 1-5 sigmatropic. Let's see if we can understand that. So here's the reactant, and here's the product. The bond that's broken is right here, and the bond that's formed is right here. So again, you can see you will have to carry careful analysis and observations of your reactant and products for these pericyclic, especially sigmatropic reactions. So here's the transition state, which we'll use for numbering or describing the type rearrangement. So here's a bond that's been broken. So it's 1, 2, 3, 4, and 5. Here's the bond that's been formed. So we have here hydrogen 1, and it's the same hydrogen. So the bond is broken here and formed here. So it's number 1. So the separation here is 1. The separation here is 5. So it becomes a 1, 5 sigmatropic rearrangement. So the name of this type rearrangement is a 1, 5. Once again, because the bond that's broken here is right here, so we start numbering. So the separation between the bond that's being broken and formed is 5 atoms, and the other one is just 1 atom, because here it is, just 1, so it becomes a 1, 5 sigmatropic rearrangement. Okay, let us apply that now. So here's another reaction, which is a sigmatropic rearrangement. How do we know that? Because here is a sigma bond, and it's not here. Here is a sigma bond, and it's not here. So this bond is being broken, and this bond is being formed. So it's a sigmatropic rearrangement. This, of course, as you know, these reactions here have names. So this is known as the Claisen rearrangement. Claisen rearrangement. Okay, why I'm emphasizing that is we'll discuss the Cope rearrangement in a minute. But let's not get too bogged down with the names right now. Let's concentrate on the reactions. So here's the bond that's being broken, and here's the bond that's being formed. So if you push arrows or use arrows to show electron movement, here it is. So the transition state, if you were to draw the transition state, would be O. And here we have a bond that's formed, and a bond that's broken, and a bond that's being formed, and a bond that's being broken, and a bond that's being broken, and that's formed, and that's being formed right here, and a bond that's being broken right here. So this would be your transition state. We typically put a double dagger just to indicate it's a transition state. Notice again, cyclic with 6 electrons, 2, 4, and 6 electrons in this ring. So therefore this is the product for this sigmatropic rearrangement with this as the transition state. Let's look at another example, a couple more examples here. This is another sigmatropic rearrangement. So here are 6. Here's the bond that's being broken because it's not here. And here's the bond that's being formed. It's formed here, but not here. So we can draw the transition state, and we can predict the product. Here's another reaction. This is a sigmatropic again. So you should be able to classify these pericyclic reactions as cycloaddition, or as electrocyclic, or sigmatropic. So here is a bond, and it's not in your product. Notice it's gone. But here's a bond that's in your product, so that's another type reaction known as a sigmatropic reaction. These reactions are known as the Cope rearrangement, or the Cope reaction, because they involve just carbons. So let us look at this in a little more detail in the next slide here. So here's the same reaction here. It's a 3,3 sigmatropic again. Of course, you can draw the transition state and number them, and you'll see that it's a 3,3 sigmatropic rearrangement. Here's a transition state here where the electrons are moving here to form a bond here, the double bond. This bond is being broken, so we have a partial bond here and another bond being formed right here. So this is a 6-membered ring transition state, cyclic transition state, very stable, and it gives this as the product. Let's look at the other one. So here is the other one, same reaction here. So this reactant here gives this as the product. We'll discuss this in a second. So this is the product because this is a bond here that's not here. This is a bond that's not here, but here, and of course our double bond moves. So here's an analysis of that reaction where we have electrons moving in and out. Here's our 6-membered ring transition state, very stable because of the 6-membered ring, and here's the product. You should notice here that the product is an enol. E-N-O-L, because here's the en and here is the ol. So it's described as an enol. In chemistry, these enols are not stable. They quickly tautomerize to give the keto form as we've shown here. So this Kt represents the ketoenol tautomerization to give the more stable ketone as shown here. So this enol gives the ketone. Let's see how that happens. On this slide here we have the enol, which gives the ketone. So as you can imagine here, these electron moves in, these electron move in to form this intermediate, not stable, as you can see, because it's charged. So we'll have a proton transfer from here to neutralize this carbon, and that gives the ketone. So we call this step a proton transfer step because this is charged and not stable. So the proton quickly goes from here to the conjugate base here to form the ketone, a very stable product. This is the end of chapter 18. I know it's a very involved chapter. It introduces material that's new chemistry. So you'll have to read through this very carefully and take your time to work through this lecture and the previous lecture. And of course, have your notepad and work these through. Work the problems in the book and also work the problems in the tutorial. Make sure you understand what's happening. Make sure you can find the bonds that are broken, the bonds that are formed. Because it's important to understand how these reactions work so you can predict the product. Not only predict the product, but predict the appropriate stereochemistry of the products. So once again, as I've always concluded, by reminding you that we're not just here to learn the concepts and the facts, that's important, but we're here to learn how to apply these concepts and facts to solving problems, because we are scientists. So continue to study hard, and I'll post more information on D2L.